everyone. Welcome to webinar 3 of the Slide2 Maintenance Plus webinar series. This webinar will cover support and probabilistic analysis. Just a reminder, if you have any questions during the webinar, please type them into the questions box. And we will release the recording. You can follow us on YouTube or LinkedIn to get notifications about that. My name is Bridget. I'm a geotechnical software developer at Rocscience. I'll be presenting today with Dr. Sina Javan-Koshdel, who is a geomechanics specialist with us. Basically, today we'll cover support analysis and probabilistic analysis as it stands, and we'll talk about the new features that just came out with the Maintenance Plus release in both support and probabilistic analysis. So I'll kick us off with support analysis. This is the list of all the different types of reinforcements you have available in Slide 2. So there's the typical ones such as end anchor, geosynthetics, grouted tiebacks, etc. Pile, micropile we have with 3 different failure modes. For example, the Ito and Matsui models piles with plastically deforming ground around them. Equivalent fluid weight was actually a request by one of our customers in California, where it's a common pile type. We have soil nail, launched soil nail. Launched soil nail is a soil nail that's launched into the soil in cases where the slope might be almost failing. And the launcher was actually originally used to launch chemical weapons. We also have RSPile, which integrates with our RSPile software. Sina will talk about that. And if none of these suit your model, you can define your own using the user-defined. First, we'll cover some basics. The slip surface has to intersect your support for the force to be applied. So on the left, the support does not intersect the slip surface, so there is no impact on the results. On the right, it intersects, so the force is applied. This is what the dialog looks like, where you define your end anchored and your grouted tieback just as examples. You'll notice that both of them have force application options, and both of them have force orientation options. These are found in all the supports. So we'll talk about those. Before we talk about those, let's talk about how the force that's applied is actually calculated. So what you see on the right here is called the support force diagram. This describes what force is applied at at specific increments along the support length. So if you look at the bottom one, for example, this means that this is the support, this line. If the slip surface crosses here, this is the force that's applied. If it crosses here, that's the force that's applied, and so on. So looking specifically at end anchored, for example, so I'll just go back to the slide. We see the inputs are anchor capacity and spacing. So the force applied is capacity divided by spacing. It's very simple. It's 100 in this case. So the force diagram for that one is just a straight line. Along the length of the support is the same. For something more complicated, like a soil nail, we consider 3 different failure modes: stripping, tensile failure, and pullout. So stripping describes a situation where the slope has failed, but the support remains intact in the slope. Tensile is self-explanatory, and pullout describes the situation where the slope fails and pulls the support out with it. So basically, we consider all 3 failure modes, depending on the support, and take the lowest force out of the 3 to consider the worst case. So if this is a support, for example, it might turn out that the lowest is the stripping force for this part, tensile for the middle part, and pullout for the latter part. And when you use a user-defined support, basically you're just inputting your own support force diagram. So now let's talk about active-passive. Like I said, for each support, you have to select active or passive. So we know factor of safety, generally speaking, is the resisting forces divided by the driving forces. So now the question is, where does the support force go? We can either subtract the support force from the driving forces, or we can add it to the resisting forces. Active is when we subtract it from driving. Passive is when we add it to the resisting. There's a lot of debate on this topic on what you should use with what support. Basically, it's up to you. Typically, we would say something like, for a grouted tieback, because the force of the support is applied before movement occurs, then you subtract it before the driving forces, for example, but it's up to you. So then the other one was force orientation. In this image, this is a single slice from the analysis. This is the bottom of the slice. So once the force is determined, you have to decide in which orientation it's applied. It can be applied parallel to the reinforcement. So this is a geotextile, for example. It can be applied parallel. It can be applied tangent to the slice base, or it can bisect the tangent and the parallel, or you can put your own custom force angle if you have a super specific case. For something like end anchored or grouted tieback, usually it's just parallel to the direction of the support, but you still have these options. For something like geosynthetic, where the force applied changes as the slope, as there's displacement in the slope, you might want to take advantage of these other options. So now we're going to focus a bit on geosynthetic specifically. So this is the geosynthetic support type. You use this to model geotextiles, geogrids, and so on. We've already covered the force application and the force orientation. Now we'll talk about some of the other input parameters. Strip coverage, for example. So geotextiles are laid out in strips or sheets into the slope, if you're looking at it in the software, for example. And they can be laid out side by side, or there can be a space in between. So the strip coverage is the length of the strip of geotextile divided by the length of the strip plus nothing space. So basically that means if they're laid out side by side continuously, the strip coverage is 100%. So that's what you would input there. Another input is anchorage. These are the 4 types of anchorages you can have: slope face, embedded end, both ends. This is how it's anchored to the slope, and how it's anchored determines which failure modes are considered. Now you see there's another button here called common types. So this is new in the maintenance plus release, and if we click on that, we see something like this. So this is a huge database of real manufactured geosynthetics. We've collaborated with several manufacturers and put all the data here. So you have like tensile capacity, reduction factors, etc. So you just select the one you're using. Sina will talk in more detail about this, so I will just give you a list of the different manufacturers. So we have ACE Geosynthetics, Geosyntex, Husker, McAfee, Tenkate, and Tensar International. And now I'll pass it on to Sina, who will show you some real examples.
Hi everyone, my name is Sina Javan Khoshtel, and I'm going to continue the presentation with an example of a geosynthetic reinforced retaining wall. Please type down your questions in the question section whenever you have a question, and we're going to try to respond all of your questions. Okay, let's continue. This example is a case study published by U. Bathurst and Allen. There are 2 retaining walls here. We're gonna model wall C. The procedure to model this wall is I'm gonna import the DXF file. We had the image as well. You can either use the image wizard option in the slide software, or if you have the DXF, you can import it. I prefer to import the DXF for this example. Then I'm going to import the material properties, define geosynthetic layers using the common types, add different support patterns. You can see we have different support in different colors. So there are different patterns. I'm going to add them, compute and interpret. One thing that I'm going to focus a little bit today is going to be the integration between the Slide software with other Rocscience software packages, including Slide3, RSPile, and RS2. For this example, I'm gonna drag and drop the model that I'm gonna create in a Slide2 to Slide3, and I'm gonna quickly show you the results of a Slide3 and compare the 2D and 3D results. Okay, let's go to the Slide software. This is a fresh Slide 2D software. I'm gonna import a DXF file that I prepared. So when you import the DXF file into the Slide software, here is a smart. It found that we have external boundary and we have material boundary. You have other options as well. Like when you import the DXF file, you can assume it's a water table, piezometric line, tension crack, anything. So now we have material boundary and external boundary. Also, as a default, the software runs a geometry cleanup after import. When you have several vertices in your geometry, it's going to clean up the geometry for you and make it simpler. So when I hit OK, this is the geometry that I imported. If I go to the material properties, these are just the default materials of the software. So we don't have any material defined. I have a file prepared, so I can always import the properties from another file, which is the same example, but the final version. I have two options of importing materials, which I'm going to do, and importing supports. I can do this, or I can define the supports. I prefer to define the supports here to show you how to do that. Then we have an option, assign properties. You can just select the property in this dialog and click on the model, and you can simply change the properties everywhere. And this is the abutment, and this is done. Now let's go and define the support. I'm gonna call the support, we have three different support types. I'm gonna define it as geosynthetic 1, geosynthetic 2, and geosynthetic 3. For geosynthetic 1, we select the geosynthetic type here, and then we go to common types. What happened in the real model, for the first layers of geosynthetic on the bottom of the wall, we had stronger geosynthetic layers, and as we went up, we reduced the strength. By strength, I mean ultimate tensile strength of the geosynthetic. So for this one, I'm gonna select Tensor International, RE, and 580 for geosynthetic 1. This is the ultimate tensile strength, but what we use for the analysis is the allowable tensile strength. So what is the allowable tensile strength? Is the ultimate tensile strength divided by the product of a creep reduction factor, installation damage factor, and chemical deterioration factor. So you can either put these numbers, these are the recommended values from the manufacturer. You can, based on the material that you have, you can change these parameters, or you can put it manually. It's up to you. So for the first one, I selected the 580. Next one, common type, Tensor International, RE560, a little bit smaller ultimate tensile strength. And last one, it's again a little bit weaker, and 520. So we have three different types defined. Now let's go and add the pattern. We can add the support like single supports or add support patterns. I'm gonna use the support pattern. They're gonna be horizontal. The length is gonna be 9 meters. And the spacing is 0.6. 0.6 is recommended by standards, and this is the value that it's used in the published paper. So I'm gonna use the same values. So when I hit OK, I can just add geosynthetic layers. So still geosynthetic 1, another pattern, then we go to geosynthetic 2, and this is the last pattern, geosynthetic 3. The patterns are added. Now let's go to the project setting, select the method that we want to do for the calculation. I prefer Spencer, so for this example, I select the Spencer. The next part is to define the surface options, search options. I always go for non-circular cuckoo search with a surface altering optimization technique. to find the critical slip surface. This one is set as well. One thing about geosynthetic reinforced retaining walls or slopes is that because this material, let's look at the material of the wall, is purely frictional material. For this type of material, sometimes we have very shallow failure mechanisms. In a slide, you define these slope limits, which is the limit of your critical slip surface. So your critical slip surface has to be in this limit. To make sure that you have a deep enough failure surface, you can define two limits. In this case, this limit is going to be the exit point of your critical slip surface, and the top one is going to be the entry point. So in this case, you make sure that your failure surface is deep enough. Another way of making sure that your slip surface is deep enough is to define the minimum depth. You use these surface filters options that we have in the search method. So everything is set. I'm going to save the file somewhere, probably on desktop. Then I'm going to compute the model. So when it's computing, you can see that it starts with the cuckoo search, and after cuckoo search, which is a global optimization technique, it goes to the local optimization, which is the surface altering optimization. It's done. It's quite fast. If we want to look at the results, we go to the slide interpret to open the results. This is our critical slip surface factor of safety of 1.53. There are different options. The first one is to look at all the slip surfaces that we search. You can see these many slip surfaces that we searched to find the critical slip surface, and you saw that how fast was the software. Sometimes for design purposes, you want the failure band, you want the region that we have all the critical slip surfaces. To do that, we use the filter options. Let's say I want to see the slip surfaces with the factor of safeties of less than 1.8. When I hit OK, you can see this is the failure band for all the surfaces with this range of the factor of safety. The other thing is you can look at your support force diagram. If I zoom in, you see two different colors, green and red. Red is the for the tensile capacity, and green is the for the plot capacity. So you can see for each elevation and for each reinforcement layer, what is the tensile capacity and what is the plot capacity. As I mentioned at the beginning, I'm gonna drag and drop this model that I created to the slide software. So you just need to select the scenario that you want to open in the slide tree. And one more parameter that you need to add is the extrusion depth. I select 100. And it says it's been imported successfully, and now you can see your model, your 3D model. It's very simple, very fast. These are your geosynthetic layers that they are hidden. I can unhide all of them, and these are three different material layers. We had a series of Slide2 and RS3 webinars. You can follow Rocscience YouTube and watch all of them. We talked a lot about support, search, everything. So to save some time, I ran this model in advance with the same method. The factor of safety is 1.77, and this is the 3D critical slip surface. There are different options again in a Slide2. I'm not going to go to the detail. The only thing that I want to show you is the safety map that we have in the Slide2 software, which shows you the weak region that you have in this model, which is this region that you define. If I go back to the presentation, I want to compare the results of 2D and 3D. Basically, this view is the 2D view of a Slide2. You can see that the shape of a slip surface is quite similar, both external going behind the reinforced zone. But factor of safety in 2D is 1.53 and in 3D is 1.77. When you extrude a model like this, you expect to get similar values of factor of safety. But why here we have a factor of safety of Slide2 20% larger than a Slide2? The reason is that in 2D, you assume that your critical slip surface goes beyond the reinforced zone. But if you model it in actual 3D, you can see that it's impossible because you extruded the reinforcement layers, and you definitely have intersection with the reinforcement zone at 2 points, one here and one here. And when you bring the strength of the reinforcement to the factor of safety calculations, you get higher factor of safety, which is okay because we are modeling a 3D, actual 3D geometry, and we are not just assuming that the slip surface goes beyond the reinforcement. Okay, the next part is piles for slope stability analysis. We have pile and micropile option, and we have another option which is an integration between the Slide software and RSPile software. RSPile is a standalone software for pile analysis using a finite element engine, and we can use the results of this pile analysis, bring them to the Slide software, and do the slope stability analysis. The way that it works is, the concept is, when you have a uniform displacement applied to the support from the slip surface, you can use this displacement and the angle of the displacement to find the lateral and axial resistance of the pile against sliding. So this is what we do in a slide. We get this displacement due to the critical slip surface, and we assume that the angle is tangent to the critical slip surface, the angle of the displacement, take it to the RSPile software and find the axial and lateral resultant force of the pile against the sliding. So for the axial one, the orientation of the force is parallel to the pile, and for lateral one is perpendicular to the pile. This is some of the graphs that, for example, for laterally loaded pile, we can get beam shear force, and this is the sliding depth. So for that depth, we pick the numbers, take to a slide, and do the analysis. Okay, we have an example here. In this example, we define the soil profile in Slide2, the same soil profile in RSPile, and define RSPile cases with axial, lateral, and axial and lateral case studies. And then we create different scenarios, compute and interpret, and see what happens. The initial file that I created is this one. It doesn't have any pile. So I'm gonna go and define the support properties for this one. Let's say it is axial and lateral. I select the RSPile option. When you select the RSPile option, you can choose the file. This file is the file that is analyzed by the RSPile software, which is this one. So if I open this one, the software is going to import the RSPile parameters. So we can match the material properties in RSPile and Slide. So dense sand and soft clay. Now the material properties, they match. Before I continue, I'm going to open this RSPile model. So this is the RSPile software. As you can see, it's already analyzed, and you can look at the displacement. And if I want to show you what we define, this is axially and laterally loaded pile. You can also graph your pile, and these are the graphs of the pile. So this information will be transferred to the Slide software. I hit OK. I'm gonna add a scenario here. So let's save this file, and I'm gonna add a scenario. I'm gonna call it axial and lateral. Now I go to support, add support. This axial and lateral support that I added, I'm gonna add it here. So this one is gonna be 71 and 19. And another pile is gonna be 65 and 90. So the piles are added. I'm gonna save this model and hit compute. So the first scenario is with no pile. So I just want to run one scenario, which is the axial and lateral. When you run a slide and RSPile, in the first step, the software is gonna run the RSPile engine, which is the finite element engine, which is this one. After finishing the computation of for the pile, then the software is gonna add the information to a slide and do the slope stability analysis, which is this one. And we use simulated annealing with surface altering optimization. And it's done. Let me open a file that I've already computed for different case scenarios. The same file, I have two more scenarios. So if we look at the results, for the master scenario, when there is no pile, the factor of safety is 1.03. When we add the axial pile, the factor of safety doesn't change much because of the shape of the slip surface is more lateral, and this is the axial force. To see what is coming from the RS pile to a slide, if we look at the slices, you can see that this is the RS pile forces, which are axial. And also you can look at the force diagram, which is not constant anymore, and these are coming from RSPile, and it's already analyzed in the RSPile software. For the lateral case, factor of safety went up to 1.5. You can see that the resultant force is horizontal, and also the force diagram, the pile diagram is like this. And axial and lateral, the resultant force is not axial, is not lateral, it's a resultant of these two. Factor of safety went up to 1.58, and the force diagram is like this. So you can see how we can analyze a model with RSPile and a slide. I'm gonna pass the presentation to Bridget. She's gonna continue with the probabilistic analysis.
Thank you, Sina. So now we're going to switch gears completely to probabilistic analysis. We'll cover what is probabilistic analysis, why use it. We'll show a simple setup in slide 2, and then we'll cover what's new in probabilistic, which is response service. Then I'll pass it back to Sina, who will do some advanced probabilistic analysis with real-life cases. So first of all, what is probabilistic? The analysis we do now, deterministic, is when we have single parameters that we input into the analysis. For example, we say cohesion for this slope is 2 kilopascals. It's a single value, 2, and we get a single result, factor of safety. Probabilistic, instead of saying that the inputs are single values, we now say maybe there's some variability there. So here, for example, we say most likely it's 2, that's why the curve is highest, near 2, but it might be 1.5 or 1 or whatever. So deterministic, one input, probabilistic, distribution input. And what we do with probabilistic is we sample this distribution. So for example, we might take 0.7 here. We plug it into the slope and we get factor of safety for that slope. Then we get another sample, a different factor of safety. And we do this maybe 1,000 times. And we end up getting what's called the probability of failure, which is the number of simulations with factor of safety less than 1 divided by the total number of simulations. On top of that, we also still get our usual factor of safety value. So the results aren't different, we just have additional results. Why use probabilistic? People might say that my deterministic analysis works fine, so why should I introduce probabilistic? Or no real site has enough data to run probabilistic analysis. So I'm going to try to show you through 3 cases how you can bring probabilistic analysis into any analysis. So the first case will be you have meager data available, which is quite common. The second will be you have really meager data available. And the third will be you have too much data available. So in the first case, say I have 5 estimates of cohesion for a slope, 2, 4, 6, 4, 4. My choices are I can take the average, which is 4, and get the corresponding factor of safety, but this might be unconservative because I'm not taking into account the worst case, which is 2. So I can take the worst case, plug that in, and get the corresponding factor of safety. But this might be too conservative, which means expensive, because I'm assuming that the worst case is the true case. So instead of taking all my data and forcing it into one value, why not use all of the data? And that's where probabilistic analysis comes in. In the second case, I only have one measurement of cohesion, it's 3, and I barely managed to get that. So I can plug in my single value and get my single factor of safety and put all of my confidence in that one value. Or I can account for some uncertainty, and I can say, well, maybe it's 3 plus minus 1 kilopascals. And in the third case, the unlikely case that I have tons of data available, the options are the same as in case 1. I can take the average and be unconservative, or the worst case and be overconservative. But again, instead of forcing all my data into one number, why not use it all? So now let's look at how we use these 3 cases. So in the first case, 3 of the values were 4. So probably it's 4, but there were some stragglers, 2 and 6. So here, for example, I might say, okay, I can consider cohesion as being normally distributed. So probably the value is 4, that's why it's the highest. But I also want to see, what if it's maybe 1, or what if it's maybe 6? It's possible it's not exactly 4. In the second case, we said we were going to do 3 plus minus 1. So here I might take advantage of a uniform distribution. So I'm saying, I guess it's 3, but what if it's 2? What if it's 4? And in the third case, when I have tons of data, I can actually make a histogram. So count up how many 7s, how many 6s, etc. And if I have enough data, I can determine the exact distribution and plug in what looks like log normal in this case. So then why use probabilistic analysis? Basically, using probabilistic removes the blind confidence in a single parameter value and a single factor of safety. It takes into account the uncertainty that there might be in these values. It allows you to consider all of the possible scenarios that might happen with a slope, not just that single one. And again, the results you get are probability of failure, as well as your factor of safety, which we would always get. So you don't get different results, you get additional results. So how do we set this up in slide 2? The first step would be what we just did, coming up with the distributions for each parameter. So this is done in the material statistics dialog in slide, which looks like this. Here we have, in the first material, cohesion and friction angle are random, both with normal distributions. These are the means, or the most likely values, and this is the standard deviation. The standard deviation describes how stretched is the normal distribution. Then we have relative min and relative max. These describe the extents of the samples we want to consider. So mean minus min, 1 minus 0.3 is 0.7, and that's the lowest value we want to consider for this one. 1 plus 0.3, 1.3 is the highest. So we have our distribution. Now we want to sample it. And how many times do we want to sample it? That's defined in the project settings dialog. So here you might say, I want to sample this 1,000 times. You also select the sampling method, which I'll cover in the demo. So we sample this 1,000 times. So same as before, say we take cohesion as 1, we plug it in, we get factor of safety. We sample another value, we plug it in, we get factor of safety. We run 1,000 simulations. And then we get the probability of failure, which is the number of simulations with fs less than 1 divided by the total number of simulations. So to digest all of that information, I'm going to do a demo where we have this slope, which is taken from the tutorial, and we're going to make the cohesion of this maroon material follow this distribution. So I'll open up Slide, and I have it ready here. So we can look at the materials. They're all more Coulomb, and we can see this upper marine, this maroon material is relatively weak. So now I'm going to add a couple of scenarios. I'm going to right click and rename. This first one will be deterministic, which is just our regular. The second one will be probabilistic global minimum, which I'll explain. And the third will be probabilistic overall slope. So first one, deterministic as usual. The second one, I need to enable probabilistic. So I'm going to click on project settings, statistics, and check probabilistic analysis. This means it's now on. So the options I have here, I have sampling method. Between Monte Carlo and Latin hypercube, you should always use Latin hypercube. It's more accurate. Monte Carlo is more of a legacy method. It's also used in research, so you can use it to compare to research. Otherwise, Latin hypercube. Response surface, I will explain later. So in this case, I'm going to do 50 samples just for speed. Spatial will be covered by Sina. And then the last option here is analysis type. So I'm going to click global minimum. This means that I'm going to have 50 simulations, but the slip surface considered in all 50 will be the critical slip surface found in a deterministic analysis. So the slip surface is the same in all 50 simulations. The cohesion will change. Overall slope means that I have 50 simulations, the cohesion changes, but the software is free to find a different critical surface in each simulation. So this scenario will be global minimum, and I'll click OK. And then I'll click on the other scenario, the OS, and I'll do the same. Project settings, statistics, probabilistic, Latin hypercube, 50 samples, and this will be overall slope. Now I want to define my distribution. I want to define the same one in both of these scenarios, so I'm going to link them. I click link, and I link both of them. Then this new statistics menu has shown up since I've turned on probabilistic. So I click statistics, materials, and I'll click on this upper marine. So now I want to add a random cohesion here. I click the add button. And I only want to look at cohesion. So I check cohesion and hit next. And these are the distribution options I have. So this is uniform, like we mentioned. We have more advanced ones like gamma if you have a bunch of data. Here I'll just put normal and finish. So the mean is 4. It pulls this out of the define materials dialog. I'm going to set the standard deviation to 1. Now, a good rule of thumb is that this left extent of the normal distribution is the mean minus 3 times standard deviation, and the right is the mean plus 3 times standard deviation. And we have a handy button that takes care of that for you called the 3 sigma button. So that fills in relative min and relative max with 3 times standard deviation, which means the lowest possible value will be 4 minus 3, and the highest will be 4 plus 3. And I'll click OK. Since my scenarios were linked, that should have been defined in the other one too, which I will check. So I'll click on this one and statistics, materials, upper marine, and yes, it's defined. Now I can unlink the scenarios and hit compute. And click OK. So the first one is deterministic, very fast, it's already done. The second one, global minimum probabilistic analysis, it's also very fast because the slip surface is already known. So it's already done. Overall slope takes a little longer. As you can see, we're on scenario 303. That's because it's computing a different surface in each simulation. Now, while this is computing, I'm going to look at the results for the first two. So I clicked interpret. So we can look at the deterministic case. We see the slip surface goes through our maroon material, and the factor of safety is 0.996. Then I'm going to click on the probabilistic global minimum case. So now the results look a little different. We have our same deterministic factor of safety, 0.996. We have some other stuff. Most importantly, probability of failure, 88%. That means 88% out of our 50 samples had a factor of safety less than 1. Notice only one slip surface is shown because global minimum uses the same slip surface. So now we can look at results. If we click on statistics histogram, we can plot the cohesion that was actually used. So we plot that, and we see that it looks similar to the distribution we defined. The gray line is what we wanted. the blue is what we got. So most of the values are 4, like we said, and it ranges between 1 and 7. Now I'm going to right click and do change plot data. And I'm going to look at factor of safety. And I will highlight factor of safety values less than 1 and click done. So you can see almost every case failed. Factor of safety less than 1, all the orange. And the area of this orange is the definition of probability of failure. I'll close that. Something else we can look at is scatter plot. So I'm going to put x-axis cohesion value, y-axis corresponding factor of safety. And we can see, as expected, as cohesion increases, factor of safety increases. And now my overall slope analysis should be done, so I'm going to click on that. So now the probability of failure here is 94%. In the global minimum case, it was 88%. So it's higher, it's more accurate as well, because a different surface can be found in each case. To see the surfaces, I'm going to go to the display options down here. I'm going to click General, and I'm just going to turn off the material colors. So that's a little clearer. Now we only did 50 samples here, which is very small, just for the example, but we see that different global minimums were found in different scenarios. Okay, so that should give you a basic idea of how do I set up probabilistic, what do the results look like. Now we'll talk about response surface. So this is new in the Maintenance Plus version. This is the third sampling method over here. Response surface uses machine learning to train a model with a small number of samples and creates a factor of safety surface. So then the factor of safety is predicted for 1,000 samples from that surface. So basically this means that when we enter 1,000 samples here, that means we will get 1,000 factor of safety values, but 1,000 computations aren't done. It's less than that. The algorithm determines how many need to be computed to get the result. The advantage of this method is that it's orders of magnitude faster than Latin hypercube for overall slope. For global minimum, it's not worth using it. Their global minimum is already fast, but for overall slope, it's worth it. So I'm going to show you what this does through this example. This is a material with a weak layer running through it, and it has 3 random variables. So I'm going to switch to the example. Okay, so first of all, we can look at the materials. So we have this soil material, which looks like this, and this weak layer material, which has a cohesion of 0. I'm going to click on statistics. And we can see that the soil material has a random cohesion following a normal distribution. And the friction angle has a random, the weak layer has a random friction angle following a gamma distribution. I'm going to hit cancel and cancel, as well as our load has a variable magnitude. So I'm going to right click and hit statistical properties, and I can see that it follows the log normal distribution. So basically we have 3 random variables for 3 parameters following 3 different distributions, which is quite complex. So this first scenario is just standard Latin hypercube. I can click on project settings, statistics, and see it's Latin hypercube 1000 overall slope. The second scenario is exactly the same except response surface. So project settings, statistics, response surface. So again, we enter 1000 here. We're going to get 1000 factor of safety values, but for this case, only 4 computations will actually be done based on the algorithm. So I'm going to click interpret. I already computed this before. And I'm going to view the 2 scenarios side by side. And the one on the left is Latin hypercube, the one on the right is response surface. So we see that there are more surfaces found here because 1000 actual computations were done, and there are only 4 surfaces here, but they cover the same space because they're placed strategically. the probability of failure is 72.8% versus 73.2%, which is essentially the same. If we were to look at the true factor of safety in each simulation that Latin Hypercube computed versus the predicted one by a response surface, it would look like this. So you can see for every simulation, they're almost identical. The difference is in computation time, and that's the advantage. So this was a pretty simple model. It takes about 7 minutes with Latin Hypercube, 20 seconds with response surface. 7 minutes isn't a big deal, but this means that response surface got the same result in 4% of the time. Again, in slide 2, not as much of a advantage, but in slide 3, which is why we initially launched this, a 3D overall slope analysis can take 25 hours, like this slope shown here. Whereas with response surface, it takes about 1 hour. So why not always use response surface? It's important to remember that response surface gives an approximate value of factor of safety. It's very accurate, but it's not for sure. So I would use response surface, for example, as I'm setting up my model, when I'm deciding if I add support, what's the probability of failure, and so on. And then I would always run one Latin Hypercube analysis overnight. And now I will pass it back to Sina for some advanced probabilistic analysis.
Thanks, Bridget. Let's continue the presentation and talk about some advanced probabilistic analysis. Before I proceed, there were a lot of questions. Feel free to write your question in the question section. I'm gonna try to answer a couple of them related to the probabilistic analysis during my presentation. So, like, if one of the questions is if we have a spatial probabilistic analysis in a slide, yeah, this is what I'm gonna talk about. Okay. I'll answer some of these during my presentation. One question that was about overall slope stability analysis compared to global minimum and what is the advantage of global minimum. The point is, for some case studies, first, they give the same answer, exactly the same answer. But global minimum is mostly used for the back analysis. So it's a simpler method and you can do the back analysis to find the parameters, the initial parameters. The other question is, can you plot the statistics of the factor of safety curve? Yes, actually the way that probability of failure is calculated, first we create a distribution curve for the factor of safety, and then we find different parameters. This answers one of the other questions that can we define probability of failure for the factor of safety of less than 1.5? Since we have a distribution for the factor of safety, you can choose a range, either factor of safety of less than 1 or between 1 and 1.5, using the histogram of factor of safety or CDF curve of the factor of safety. What else? And one question about the different PDF cases that we have in a slide. I'm going to show that in the example. Okay, I'm going to continue. So advanced probabilistic analysis. So far, what Bridget showed was our properties, our solved parameters are independent, which means that there is no correlation between them. However, as you can see in this figure, this is from a triaxial test. Cohesion and friction angle can be negatively correlated. This is called cross correlation. It's a number between -1 and 1, and a negative one.
Hi everyone. Looks like we're experiencing some technical difficulties. Just a reminder, we're all working from home. Let's see if we can get this back up and running. Hi everyone. So like we said, some minor technical difficulties. I'll just go on here while Sina is getting back online. So cross correlation is something else we can consider in slide. This means for something like cohesion and friction angle, generally it's assumed they're negatively correlated. And you can define a correlation coefficient between parameters and also between parameters in different materials. The big assumption that we make in the probabilistic analysis I've described is that we assume that in each simulation, the value is assigned to the entire slope. So we assume, for example, cohesion is 2 throughout this entire slope, which is not very realistic. And that's where spatial variability comes in. So instead of saying this whole slope is 1, we say maybe we should divide that into smaller bits in the slope. So we assume that the strength changes within the slope. So simulation 1 might now look like this instead of homogeneous. Similarly, simulation 2. The way you set up a spatial analysis in Slide is you check off the spatial variability analysis box in the statistics menu, which I showed you previously. And it requires just one extra input as compared to regular probabilistic analysis. And it looks like Sina is back online, so I can pass the presentation back to him now.
Thanks, Bridget. Sorry, everyone, for the technical issue that we had. So I'm back now. Okay, so the parameters that we define for the spatial variability analysis is first we check the turn the spatial variability analysis on in the project setting, and then there is only one parameter that we need to define, which is the spatial correlation length, in addition to other statistical parameters that Brigitte mentioned before. This parameter is defined as the distance over which soil properties are highly correlated. If I want to explain it, it's better to show it in this figure. Let's say you have a cohesion value of mean at the standard deviation of 0.5. In the deterministic analysis, the value of cohesion is equal to 2. So we just assume that 2 is everywhere along the soil profile. In the single random variable approach, we do several samples, and for example, for the first one, we have the cohesion value of equal to 1.2. But when you do the spatial variability analysis, let's say we have the spatial correlation length of 1 meter, you can see that in every meter, our soil property or cohesion is changing. And when we have the spatial correlation length of 20 meters, we have regions of 20 by 20 with different parameters, different values of the cohesion. So this is the definition of the spatial correlation length. We have a table in the slide software to recommend some values for horizontal and vertical spatial correlation length. We're going to extend this table in the next versions. We have a huge database now. You can improve this one. So after defining the correlation length, the next step is to create different simulations. Now in each simulation, we have one spatial field. So when a simulation changes, the spatial field is changing as well. And for each simulation, we have to calculate factor of safety. This is the important part. We have a spatial field with weak and strong regions of material. And now we need a method to find the weakest failure path. If you use the circular method, circle doesn't care if the material is strong or weak. It goes through weak and strong material. But in a slide, we have a unique method called surface altering optimization technique together with other materialistic approach that actually finds the critical failure surface that goes through the weak region. And still, this is the method of slices, so it's not something weird. It's just advanced limit equilibrium method. And at the end, we calculate probability of failure as the number of cases with the factor of safety of less than 1 divided by the total number of simulations. We call this method random limit equilibrium method, which is a combination of a spatial variability and limit equilibrium method. You can just Google this term. You find a lot of papers or on Google Scholar that we published in the past couple of years using this option in Slide2 and RS2. Let's go to the example. This is a Sugar Creek embankment. In this example, first we did a deterministic analysis. Factor of safety is around 1.6. The other integration that I mentioned was integration between a slide and RS2. You can see we get the same factor of safety and the same critical slip surface by just dragging and dropping the model from a slide into RS2. In this example, we turn on the spatial statistic and we look at the different parameters. We define the cross correlation. Let's see what happens. This is the example. We have 4 different cases: single random variable approach and spatial analysis with and without cross correlation. For example, for the single random variable approach, if we go to project setting, we can see that no spatial is selected. And if we go to material statistics, we can see that different types of statistical parameters are defined. And this one has correlation. As I mentioned, we have an advanced correlation option in the slide. We can correlate almost any parameter with each other. And in this one, we correlated cohesion with friction angle with the recommended value of -0.5. For the spatial one, we have an option called property viewer. You can look at your spatial field before doing any computation and to see if your spatial field makes sense. If we look at the friction angle, for example, this is a spatial field for friction angle. And we have 50,000 simulations for this example. If I go up, you can go to different spatial fields. The other thing here is all horizontal and vertical correlation links parameters are defined for all of our material. Let's say I want to select the material at the bottom of this model, and I look at this material and I see that, yeah, this is not my field, so let's change it. The recommended change is like for horizontal, we have larger correlation lengths compared to vertical. So vertical is 1, horizontal is 100. You can see sort of layers of 1 meter horizontally. Or if you want, you can change the horizontal to 1 and vertical to 100. And you should see the vertical layers of material. And you say, okay, this is my field. You go back and you can see that the material statistic for that material, these parameters are changed. So depends on what you see in the property viewer, you can change it in the original file as well. If I want to show you results very quickly, let's just look at the spatial results, and then I'll show you a table with other results. So if we go to the property viewer again, and I'm gonna change the slip surface to a different color and make it a little bit thicker. So for this one, let's say for friction angle, this is the critical slip surface for every single simulation. You can go up and you can see the critical slip surface for different cases. For example, let's look at this one. We start from here. The search is smart. It goes through the weak region and then goes out from the geometry, from the weak region as well. Or another one, maybe this one, again, the same thing. So the combination of surface altering and spatial field is very important for the analysis. So if we go back to the presentation, we compare 2 different cases: a single random variable method without a spatial variability, without cross correlation, gives a factor of safety of 3.24. But random limit equilibrium method, which considers a spatial variability together with cross correlation, gives probability of failure of 0.01%, which is actually good for design purposes, considering this deterministic factor of safety, which is 1.6. If we compare the results of Slide2 and RS2, we don't have a spatial statistic in RS2, which is going to be added in near future. But you can take the fields as discrete functions, export it from a slide and import it into RS2. You can see that they are exactly the same, and do the analysis for one simulation. And for this one, you can see that the critical slip surface is the same in RS2 and a slide, and they give the same factor of safety. This paper is just published in GeoRisk Journal, Surface Altering Optimization in a Slope Stability Analysis with Non-Circular Failure for RLEM. Bridget and I, with some other researchers, we published this paper. It's going to be online very soon. For the first time in literature, we investigated spatial variability and limit equilibrium for case studies like Sugar Creek Embankment, James Bay Dike, not just for simple cases. This is the actual case studies. And I recommend you to read it. The other thing is, if you have other questions, Bridget and I, we have 3 hours of lecture on YouTube of Rocscience about probabilistic analysis for slope stability. And you can watch these lectures, and probably we're gonna answer a lot of your questions in these lectures. Bridget is gonna continue the presentation.
Thanks, Ina. So now we're running a little bit behind schedule. I'll just do a quick overview of what's coming soon in the Maintenance Plus release. So these 3 features. The first one is multimodal optimization. So this means that multiple failures can be found and all optimized. So this is very useful in many cases where you don't want to just look at the single most critical failure. Another is probabilistic coefficient of variation. So this means instead of making random cohesion or random whatever's any parameter like we did before, you can put the randomness on shear strength itself. So this is much easier. All you have to input are the distributions and the coefficient of variation. And the other is we're working always to improve our anisotropic algorithm. So this is working to make the search which finds the weak orientation when using anisotropy better. So these are all things coming out in the Maintenance Plus release. And I think we're a little late, so maybe we will skip the questions, but we will send out a sheet answering all of your questions to everyone who attended. So don't worry if we didn't get to answer your question. And thank you very much for attending.